I have a great pleasure to introduce Jacek Krajczok, who will speak about modular invariants of compact quantum groups. Please, the floor is yours.
Thank you very much, and thank you for the invitation. And I'm sorry that I cannot be there in person. I will be speaking about joint work with Piotr, who I believe is also in the audience, though I cannot see the audience right now. Okay, and well, I will start with the introduction. I will try to be rather quick, as well. We have seen some an introduction to compact quantum groups just 2 hours ago. Okay, so for me, compact quantum group is as defined by Professor Wronowicz. Is G, and it consists of a unital C-star algebra together with a unital star homomorphism, which satisfies two things. Well, it satisfies this class associativity condition, and second, the density condition. It is the unital star homomorphism delta is called multiplication. I will give some examples in a moment, which will justify this definition. First, let me mention that very important result in the theory of compact quantum groups, and a result that will be crucial for what I will be saying, is that there exists a unique Hare integral, which is a state on A, which satisfies this invariance condition. And throughout the talk, I will assume that my Hare integral is faithful. In other words, I'm working at the reduced level. It is with this definition, it is not always the case that Hare integral is faithful. However, you can always pass to the to a reduced level, let's say. And so I will always assume that Hare integral is faithful. Then we perform the GNS representation for this state. It is, in particular, we obtain a representation of A on a Hilbert space I denote by L2 of G. Since H is faithful, this representation also is faithful. And well, the image of A I denote by C of G. It is in general a non-commutative C algebra. Then I will be mostly working in von Neumann algebraic picture. So I will be looking at the generated von Neumann algebra I denote by L infinity of G. And then it is natural to denote the pre-dual space by L1 of G. So let me briefly give some examples to, well, first to justify the definition. If G is a compact Hausdorff group, then we have a Haar measure. We can define C of Blackboard. We can define a compact quantum group in the sense of previous definition. Well, we define the C-star algebra simply as this C-star algebra of continuous complex valued function on G. Co-multiplication is given by this pullback of multiplication. And then the Hare integral is simply given by integration with respect to Haar measure. And L infinity of G is the space of measurable bounded functions on G. We have also second dual example. If we start with a discrete group, then we can define compact quantum group Blackboard G. Algebra is the reduced group C-star algebra of gamma. Co-multiplication acts by this very simple formula on generators. Then, well, one can check that this gives us a compact quantum group, and then we obtain that this Hare integral in this situation is given by the canonical trace, and the von Neumann algebra is given by the group von Neumann algebra. We write that G is dual quantum group to gamma, and in fact, within the setting of locally compact quantum groups, one can extend the notion of contracting dual, and using this notion, the above defined G is really dual to gamma. However, it works in general. So with every group we associate its dual, and then if we take second dual, we go back. It's duality. Furthermore, compact groups are dual to discrete quantum groups. Another example that should appear here is, of course, the SUQ2 group, Q-deformed SU2. As we have seen just 2 hours ago, its C-star algebra is generated by two elements, alpha and gamma, such that, well, this 2x2 matrix is unitary. This gives us a number of relations. Then one can check that there exists a co-multiplication given on generators by this formula. And maybe I won't spend much time by discussing this example as it already appeared. However, it is very important, which will be clear soon. And because we are on a graph algebras conference, let me mention that the C-star algebra was proved to be a graph C-star algebra. The graph is very nice. It has two vertices, arrow between these vertices, and two loops at each vertex. Two loops, one at each vertex. Okay. Next, well, I will be speaking about modular theory, and what do I mean by that? Well, first, the Hare integral extends to a normal state on von algebra L infinity of G. Hence, by Tomita Takesaki theory, we obtain a continuous group of modular automorphisms, which I denote by sigma HT. And say formally, it is characterized by this condition. If X and Y are appropriately nice elements, then in general, it is not the case that Hare integral H will be a trace. However, using this, we obtain a sort of traciality condition using this modular automorphism. So modular automorphism group gives us a way of working with non-tracial states in a similar way. So it gives us a way of handling non-tracial states. To be precise, the appropriate continuity condition is point-Wickster continuity. However, this is a technical point which won't be very important for us. There is also a second group of automorphisms, which are called scaling automorphisms. Roughly speaking, they can be described using Tomita Takesaki theory for the dual discrete quantum group. Okay, so these are general results. However, because most of the time we will be interested in compact quantum groups, and then the situation gets much more concrete, in a sense simpler. Why it is the case? Well, most of all because compact quantum groups have very nice representation theory, which resemble the classical ones. I'm very lucky that some notions from this theory were introduced previously. Okay, but just to set up the notation, it is a result in the theory of compact quantum groups that every unitary representation for me will always mean unitary representation. So every representation of a compact quantum group decomposes as a direct sum of irreducible ones. Irreducible representations are finite dimensional, and I denote by IRG the set of classes of irreducible representations. And I will follow the typical abuse of notation and identify class with its representative. So for each alpha in the set IRG, we obtain honest unitary representation of a quantum group G, which by definition is an element of the tensor product. And as I mentioned, irreducible representations are finite dimensional, so we don't have to worry too much about this tensor product. It is convenient to choose an orthonormal basis in our Hilbert space, and then when we slice per functional on the right leg, we obtain elements of C of G. And these elements for fixed orthonormal basis will be denoted by U alpha ij. And in the theory of compact quantum groups, very often it is enough to calculate stuff on this matrix elements because they will span a dense subspace. Another important point is that there exists a family of positive invertible operators, rho alpha. So for each irreducible representation, I obtain positive invertible operator rho alpha. And I can use those operators to express modular automorphism and scaling automorphism. More precisely, well, rho alpha is a positive operator on a finite dimensional expert space. I can diagonalize it. And so I'm assuming that I have chosen the basis in such a way that rho alpha is diagonal with eigenvalues rho alpha I. And then, as you can see here, we obtain very simple formulas which allow us to express modular automorphism and scaling automorphism when it acts on matrix elements, U alpha ij. And in practice, those formulas are very, very handy. Okay, as was already mentioned, and actually what can be easily seen from these formulas, that it is the case that modular automorphisms are trivial if and only if all of these operators are trivial. And it is again equivalent to the condition that all scaling automorphisms are trivial. So and then we also know from the general to metastatic theory that this condition holds if and only if Haar integral H is trivial. So we have nice concrete way of seeing, well, of maybe of describing non-triviality of Haar integral using rho alpha operators. If they are trivial, then one says that there is of Katz type. This can be taken as a definition. No, there is a number of equivalent conditions. So for me, the interesting situation will be when we are in a non-Katz type situation, because then we obtain this quite rich structure relating to these two groups of automorphisms. So maybe let's quickly look at some examples. In classical case, when G is a classical compact group, then the Haar integral is trivial, of course, and we are in Katz type situation, so automorphisms are trivial. Similarly, it is the case in the dual to discrete situation, because this Haar integral, which acts on generators, well, is expressed on generators by this formula lambda translation lambda gamma is mapped to 0 if gamma is not equal to the neutral and to 1 if it is. Well, it is a trace. So all of the automorphisms are again trivial. However, probably the easiest example when we obtain non-trivial structure is the SUQ2, SUQ2 quantum group. Then I'm assuming that Q is strictly between 0 and 1. Then Haar integral is not trivial, and we have concrete formulas for this modular automorphisms and scaling automorphisms when they act on generators. Okay, so SUQ2 is a very nice example because it gives us a non-trivial modular structure. Okay, what I will be talking about, what is the goal of this lecture, is to speak about certain invariants of quantum groups, which are associated with, in particular, these two groups of automorphisms. But before I give you a precise definition, let me start with some motivation. As Piotr mentioned in his talk, we were able to construct a family of compact quantum groups such that the von Neumann algebra, L infinity of Kj, was the injective type 3 lambda factor. So lambda here is fixed, and for each lambda we obtain an uncountable family of quantum groups such that L infinity of Kj is the injective type 3 lambda factor. So it has a powers factor. All of the time I'm assuming here separability, so it is injective type 3 lambda factor. And we wanted to show that even though the von Neumann algebra is the same, we actually obtain uncountable family in the sense that the quantum groups that we look at are pairwise non-isomorphic. So of course, when it is stated as this, it's not possible. Well, this very much could be the same quantum group. However, these quantum groups that we obtain were concretely constructed. So I will give you maybe just a glimpse of how they were constructed, as it is not the main goal of the talk. So in a first step, well, we can treat R as a vector space over rational numbers. So we can choose a basis. The point here is that it gives us an uncountable family of irrational numbers which are independent over Q. And with each such a number, we associate a a cyclic group gamma j. Okay, so this is our first step. For each, we obtain a family of numbers and a set j, and in each element in the set, we obtain a cyclic group. Next, there is a quantum group G, which I won't go into details. It depends on lambda. So say we have such quantum group G, and next we construct our family of compact quantum group Kj by cross product construction. So how does it work? Well, we let discrete classical group gamma j act on von algebra L infinity of G via scaling automorphisms. Because scaling automorphisms are quantum automorphisms in the sense that when we apply scaling automorphisms and then commultiplication, it is the same as applying commultiplication and then tensor square of scaling automorphism. Because this condition is satisfied, we can obtain a compact quantum group via cross product construction. In particular, the von Neumann algebra of Kj is the cross product under this action. Okay, and then the crucial point for the here is the following property. We were able to show that scaling automorphism tau t for a fixed time t is inner as an automorphism on this von Neumann algebra L infinity Kj if and only if t belongs to the gamma j plus this cyclic group 2 pi divided by log lambda z. Okay, so maybe let me briefly explain why it is one of this implication. So assume that t belongs to this set gamma j plus this thing. Well, first of all, if t only belongs to gamma j, then it gives inner scaling automorphism basically by construction, because our von Neumann algebra is cross product. And well, the kind of defining property of cross product is that the automorphisms that you act with become inner in this cross product. And this addition 2 pi divided by log lambda z, well, it gives trivial scaling automorphisms, so we don't have to worry about it. So one implication is kind of automatic. If t belongs to the set, then the associated scaling automorphism is inner. Well, about the other implication, it uses properties of the quantum group G that we start with, so let's take it as a black box. What is important, that we know precisely when scaling automorphisms are inner. Okay, that's great. Why? Because we have chosen our groups gamma j in such a way that if we take different j and j prime, these groups that we look at, the subgroups of real numbers where scaling automorphisms are inner, they're genuinely different. And because isomorphism of quantum group would map scaling automorphisms to scaling automorphisms, and well, it would preserve the property of being inner. Well, we obtain the conclusion that our quantum groups Kj are pairwise non-isomorphic. So to sum up, we had this family of compact quantum. We were able to distinguish between them by looking when scaling automorphisms are inner. So let's make this more formal. For a given compact quantum group, let's introduce the first invariant, t tau in G, to be the set of those real numbers when the scaling automorphism is inner. Well, why stop there? We can also look at two other subgroups of real numbers. Namely, we can look at those times when scaling automorphism is trivial or approximately inner. And we denote the invariant using subscripts which correspond to this condition. So if there is nothing, we look at those times where scaling automorphism is trivial, inner correspond to inner automorphisms, and overlying inner correspond to approximately inner automorphisms. Okay, well, we have 3 automorphisms, but well, if we want to study what kind of invariance we can extract by looking at this modular structure of a quantum group, we can, why not look also at similarly defined invariants for modular automorphisms. So again, we have canonical state, Hari integral. It gives us a canonical group of automorphisms. So let's look at times where these automorphisms are trivial, inner, or approximately inner. Let me mention that this invariant of the times where modular automorphism is inner, it is precisely the con-T invariant of von Neumann algebra infinity of G. So it depends, in particular, it depends only on von Neumann algebra. However, well, it is very much the case that we can have the same, well, we can have 2 different quantum groups with the same von Neumann algebra, and then T sigma G invariant will be different. So we look at those really as invariants of quantum groups. Okay, so for a compact quantum group, we define 6 invariants. But well, why stop there? So far, everything made perfect sense for locally compact quantum groups. So let's make the analogous definition of 6 invariants for general locally compact quantum group. But now we also have, well, another object, namely modular element. And we can define last one, I promise, invariant, which consists of these times where the modular element raised to power it is trivial. Because I will be focusing on compact quantum groups, I don't want to go too much into this direction. However, let me just say that modular element is a certain strictly positive operator on L2 of G, which is affiliated with L infinity of G, meaning that, well, it can be unbounded, so it cannot belong to the von Neumann algebra infinity of G, but when we apply a measurable bounded function to it, via functional calculus, we obtain element of the von Neumann algebra infinity of G. So, well, you should think of L infinity of G as set of bounded functions, and then delta is possibly unbounded function on the same space. So we have, so for given locally compact quantum group, we have associated 7 invariants. And really they are invariants in the sense that they depend only on the isomorphism class of G. Well, because if we have H and G, which would be isomorphic, all of this structure would be translated. So we would obtain the same sets. Okay. But, well, with each quantum group, we can associate its dual. Possibly it gives us more invariants. So let's look at whole 14 subgroups of R. Okay, this is definitely superfluous in the sense that there are some easy reductions. First of all, when we look at T tau, namely the invariant consisting of times when the scaling automorphism is trivial, it is the same for G and its dual. Similarly, if we know T tau invariant and mod invariant for the dual quantum group, we obtain T sigma invariant for G. Maybe I won't go into details, but it quite easily follows from these properties that I have written here, and they are well known in the theory of locally compact quantum groups. Maybe there is some argument to be made for one of the containments in the second property, but this is nothing too deep. So there are some reductions in general situations. We don't have 14 groups, we have 11. It is enough to look only on T tau G and we don't have to look at T sigma. But okay, so this is general situation. Let me now go to more concrete situation. I will be interested in compact quantum groups. So now more things become easier. First of all, modular element, which arises using the radon-Nikodym derivative between left and right Haar integral. It is trivial because, well, the Haar integral on a compact quantum group is both left and right invariant. Compact quantum groups are unimodular, and the modular element is trivial. So there is not mod of G invariant, or in other words, it is trivial, not interesting. Furthermore, the von Neumann algebra of measurable bounded functions on a dual quantum group, which is discrete, has very simple form. It is simply a product of matrix algebras. And then, well, one can quite easily show that it implies that modular automorphisms and scaling automorphisms on these discrete quantum groups have to be inner. In particular, approximately inner, so we are done with, again, 4 invariants. It is not the case that all automorphisms of this von Neumann algebra are inner, but because we have continuous family, you can argue this. Okay, so for compact quantum groups, we have just 6 invariants, and in the situation that I will be speaking about later, namely Q deformations, von Neumann algebra L infinity of G will be semi-finite. Hence, all modular automorphisms are inner, and we are left with 4 invariants. Okay. So in the second part, I will be interested in actually calculating this invariant for Q-deformed compact semi-simple simply connected Lie groups. But before I go there, let me mention one more motivation, namely a question that arose when we started looking at those invariants. The question goes as follows: assume that we have compact quantum group which is second countable, and assume that all of the scaling automorphisms are inner. So theta in invariant is equal to R. Is it the case that G is of Katz type? This question is very similar to a result in von Neumann algebra theory, where which says that if you have a von Neumann algebra with separable predual and T invariant is trivial, namely all modular automorphisms are inner, then your von Neumann algebra is semi-finite. So this is kind of a quantum group analog. The second countability assumption is needed, as you can come up with some pathological examples without it. But okay, so far we don't have any counterexample, and I hope and believe this should be true. So far we have partial results, and this is a content of ongoing work. So equivalently, we can ask the following: assume that G is second countable and not of Katz type. Can we show that there is a scaling automorphism which is not inner? And we obtain affirmative answer in special situation. Well, one special situation is when there exists a 2-dimensional representation which has larger quantum dimension. So in a sense, this unitary representation is a witness to the fact that your quantum group in question is not of Katz type. So under the assumption that there will be non-inner scaling automorphisms. Another situation where you can prove this is under type 1 situation, in particular in Q-deformed situation. We have also results for free unitary quantum groups and under certain ICC type condition. Okay, now I would like to, unless there are questions, if not, then I would like to go into describing our results in the situation of Q-deformed compact semi-simple Lie groups. Okay, maybe I should start with two remarks. One remark is that I find the theory of Q-deformed Lie groups beautiful and very, very interesting. However, I am definitely not an expert in this, and I'm kind of learning as I go. So keep this in mind. Second, the construction of Q-deformed compact semi-simple Lie group is quite involved. So probably I won't be able to. Well, if you haven't seen this, I probably won't be able to give you a very in-depth, precise introduction. The point is that for each such Lie group, simple connected, semi-simple compact, we can construct a Q-deformed compact quantum group, which is denoted GQ. So all of the general theory of compact quantum groups that in particular was mentioned before holds. But using the structure of Lie group, and in part, more precisely, Lie algebraic structure, we obtain more concrete information about what's going on in this theory. So if you haven't seen this before, then probably you can skip to next two slides. But for those of you who have seen it, quick reminder and also setting up annotation. So G is as I just mentioned, then math frac G will be the complexified Lie algebra of our Lie group. We choose a maximal torus, which is isomorphic with T to power R, so R is a rank of G. It's complexified Lie algebra I will denote by H. Then we choose root system. Well, we obtain a root system, we choose positive roots and simple roots. Wave group, fundamental dominant weights, special vector, and lattices and positive cone. So as you can see here, there's a lot of structure, which, will appear in the formulations of results. However, even without knowing before what are all of these objects, you can get some grasp on the results that we can obtain. Yes. In particular, what will be important for us is the weight lattice and positive cone, as positive cone will correspond to representations. So in general situation, we obtain all of this extra tools, extra gadgets. But if you choose some concrete group like SUN, then these objects become quite concrete. You can find in the literature very concrete descriptions of these lattices, vectors, Weyl groups, and so on. So this is quite nice, as it gives you after Q deformation, you obtain interesting quantum groups, very non-trivial, in which, on the other hand, you can do some concrete calculation using this Lie algebraic objects. Okay, so 2 words on how GQ arises. So let's fix Q strictly between 0 and 1. And then we define a Q-deformed enveloping algebra of G. So it has generators and relations. I won't bother writing down relations, they are quite complicated and won't be of use here. However, we have generators which are denoted by E, F, K, and K inverse, and we obtain such a generator for each number I between 1 and rank. And one can define Hopf star algebra structure on this space. And again, I won't give you the formulas, as I don't want to overload it even more. What an important notion is that if we have a star representation of this Hofstar algebra on some Hilbert space, say, then a vector is said to have a weight denoted by Wt of xi. It is element of this weight lattice when elements ki act on this vector in this very simple form, namely multiply this vector by a certain number. So q to certain power, and this is inner product in H star. So the point here is that weight vectors are eigenvectors for all of ki's. Then important result is that we will be, well, one is typically interested in star representations of UQG, which can be written down as a direct sums of weight spaces, namely spaces which consist of weight vectors. So, and we assume finite dimensionality. So this is the family of representation one is interested in, and they are in bijection with this positive con. Finally, what defines Hofstar algebra of polynomial functions on compact quantum group GQ as matrix coefficients of the star representations, and by definition, this is a subspace of the dual, the UQG. Okay, let's go back to quantum group world. After completion, so using this Lie algebra structure, we defined Hofstar algebra, Pol Q of G, Pol GQ, which we can complete to a sister algebra, and one can show that this is indeed a sister algebra of continuous functions on a compact quantum group. What we need from the previous discussion is that, well, Pol GQ is always spanned by matrix coefficients of irreducible representations, but now we know that these irreducible representations are in bijection with the positive con. So we can look at elements of this form. This is now my notation for the matrix element of pi representation, and we slice with vector psi and theta. In fact, we can, because we are looking only at span, we can assume that these vectors have weights. So this is our nice family of elements in sister algebra to look at. They precisely correspond to U alpha ij in the previous notation. By definition, to make connection between maybe this more familiar picture, at least for me, and the previous one, by definition, we had Pol GQ was defined to be a certain subspace of the dual space to UQG. So we have this pairing, canonical pairing is given by evaluation. And in this picture, so when we take element in the Q-deformed enveloping algebra of G, we should be able to pair it with element of Pol. So what is the number that we obtain? And the answer is very simple. We apply our representation pi to element x. This is a bounded operator on H pi. So we act on a vector, take inner product with the other vector. So in this notation, the pairing becomes very simple. All right. So I gave an epsilon of definition of construction of Q-deformed compact semi-simple Lie algebra. So we have for each such Lie group, we obtain quantum group GQ. In particular, we can take SUNs, which gives us already very interesting family of quantum groups, SUQNs. And as far as I know, well, I already mentioned that SUQ2, C of SUQ2 is a graph system algebra. As far as I know, this won't be the case for SUQN for higher rank N. However, what I've learned from Marco Matassa, and I believe this to be unpublished result, however, I may be, well, that's to my knowledge, that for SUQ3, we don't obtain graph system algebra, but we do obtain higher rank graph system algebra. Okay. And maybe just also let me mention that Marco Matassa together with Robert Juncken were able to show that all of GQ will be also higher rank graph C algebra, however, not for positive Q, rather in a crystal limit. So I admit that I'm not too familiar with these results, but if you find this interesting, then go look for Marco Matassa and Robert Juncken. Whether all C of GQ are higher rank graph C algebra, well, to my knowledge, this is not known unless there are new developments. Okay, so we have this very nice family of compact quantum groups, and our aim is to calculate all of the invariants, all of the modular invariants for this family of quantum groups. First useful result, which is probably not too surprising, is that we have this canonical matrix elements. So our general theory tells us how to act on such matrix elements using modular and scalar automorphisms. This is under the assumption that the corresponding vectors are basis vector which diagonalize rho alpha operators, and when we choose psi and eta to be weight vector, this is precisely what is happening. So we do obtain that they are eigenvectors for these operators, and the numbers that we multiply with can be concretely expressed. So let me remind you that rho was the weight vector, and weights of psi and eta are some elements of the weight lattice. So everything sits in the space dual to H. So we can take inner product. So in the end, this is some number which depends on the choice of weight vector psi and eta. We raise it to multiply by 18, raise q to this power, so we obtain some complex number of absolute value 1. And this is quite useful. There are also some technical points. There are some assumptions to be made on the inner product. Okay. So this formula, in a sense, gives us information about scaling automorphisms in particular, but in a sense, it is a local. In the sense, what do I mean by that? It gives us a way of computing scaling automorphisms when we act on a single matrix coefficient. It is quite useful for computations. However, using this formula, it's not at all clear to me how can we see when scaling automorphisms is inner or not inner. So, and this is after all what we are after. So for this, we need some form of global picture of how scaling automorphisms act. And this global picture will be provided to us using theory of type 1 quantum groups. And for this, I need to introduce two results of Soibelman and Reshtikin-Yakimov. Let's start with result of Soibelman. He was able to very concretely describe all irreducible representations of the C algebra C of GQ. So what is the answer? Well, all these irreducible representations up to equivalence are parameterized by number in the torus and element W of a while group. So while group is finite. Okay. So the corresponding representation.
Sorry, Jacek, just send it to check. When you say representations, mean representation of the C-star algebra, not of a quantum.
Yes, exactly. So that's why they are parameterized by something in a sense continuous. Right, these are compact quantum groups, so representations of a compact quantum group should form in a sense discrete set. However, representation of a C algebra could have some continuous structure. In a sense that here we parameterize it by torus times finite set. Okay, so the corresponding representation, irreducible star representation, is given by convolution of pi lambda and pi w. So what is pi lambda? Pi lambda is a family of, well, for each lambda in the torus, pi lambda is a character on the sister algebra, and on our generators, matrix elements, it is given by this very simple formula. We take inner product between vectors and we take pairing between weight of xi and lambda. And what does it mean? Well, by definition, weight of xi was element in the weight lattice. Weight lattice can be identified with the dual group to the torus. So torus is compact abelian classical group. We can take dual group. It will be isomorphic with z to the power r. So we have pairing between abelian group and its dual. Okay, so this is family of characters. And so this is one ingredient in pi lambda w. The second ingredient, well, for each w, pi w is a representation on tensor power of L2, and they are built using canonical representation of SUQ2. I don't want to go too much into these details. Maybe think that for SUQ2, this representation that we look at is that lambda is a weighted shift, and Q acts in the basis of L2 of Z plus by multiplying by Q to power K. So this is the sort of canonical irreducible representation. And then using the fact that Lie algebra or deformed Lie algebra of SU2 embeds into Q-deformed Lie algebra of G, you take pullback, so you obtain a family of irreducible representations, and then you glue them up by seeing how this veil group element looks like. The point here is that
you obtain the star homomorphism from CGQ to CSUQI2 by taking a pullback from this universal enveloping Lie algebra picture. Am I right?
Yes. Yes.
This is what you just said, right? Okay.
Yes, exactly. I guess you have to justify that it passes to completions, but
yeah.
That's exactly what is happening, and that's how you should think about it.
Okay, thank you.
So this gives you a family of characters, family of irreducible infinite dimensional representations, and then you obtain everything by taking this convolution of those two things. So pi lambda w is representation on, sorry, I forgot a tensor product symbol. It's a representation on some tensor power of L2 of Z plus. Okay, so result of Soibelman gives us a concrete description of all irreducible representation of sister algebra C of GQ. In particular, the sister algebra is type 1. Next
Sorry,
result.
in which year did he prove it? I mean, Soibelman? Just roughly, I don't want to place it.
Well, I would guess something like 2000s, but I would have to check it.
Okay.
But it's not new.
Okay. I think it was even before 2000, and it's Korogotsky-Soibelman.
Well, I checked it, and in their paper, they reference to a single author paper of Soibelman.
Oh, okay. All right. Sorry.
Another result that we need is a result of Reshetkin-Yakimov, which describes Hart integral on compact quantum group GQ. Though I will be using not their notation of Kennedy Kumar. However, so GQ is a compact quantum group. So it has a Hart integral, which is a state. And we can give a very, or rather they were able to give a very concrete formula on how to calculate this integral. So what is happening here? Let's take X in sister algebra C of GQ. Then we multiply it by a certain element, apply representation, one of these irreducible representations, take trace and calculate integral. So some of this, I need to explain some of the symbols. The lambda is simply the normalized Lebesgue measure on the torus. W0 is longest element in W. So just canonically chosen element in the value group. So this gives us a family of irreducible representations. B-row is certain, again, canonically chosen elements in pole of GQ. It plays a very important role. I don't have time to go into details. It is canonically chosen, and in the case of SUQ2, you can calculate it. It's minus gamma. So now we have element in assisted algebra. We multiply X by it, apply irreducible representation, calculate trace, take integral. So this formula should make sense, at least. There is also normalization constant, but it doesn't matter for us. So we obtain so we have concrete formula for the high integral, and from this, it is not too far to describe Plancher measures and all of the objects that appear in the Desmet's theorem. So though there are things to be checked. So Desmet's theorem is a general result in the case of type 1 quantum groups. In this specific situation, what we obtain is a unitary operator between L2 of GQ and a direct integral of the family of the space of Hilbert Smith operators on H lambda. So the Hilbert space corresponding to representation pi lambda W0. And its property, well, there are lots of properties, but one of the important properties is that if you conjugate your von Neumann algebra of measurable bounded function on GQ, you obtain something very simple. You obtain simply direct integral of B of H lambda tensor 1. So they act on the space of Hilbert Smith operators by left multiplication. Okay, I should hurry up, I guess. To sum up those two previous results, we have a concrete description of irreducible representation of the sister algebra, C of GQ, concrete description of the Hare integral. Using this, we can look at this quantum group as, rather the dual discrete quantum group as type 1 quantum group. This allows us to shift picture from the general abstract situation where we have L2 space to direct integral picture where things become more concrete and easier. In particular, I will now neglect writing this isomorphism. An element in L infinity of GQ can be written as a certain direct integral. Together with Piotr, and this was an important ingredient in our work, we were able to give a concrete expression of the action of scaling automorphism on such an element. And the concrete answer is as follows. So let me maybe describe what is happening here. So X is given by direct integral of X lambdas. If we apply scaling automorphism, two things happen. First of all, X lambda, well, turns to X lambda lambda 2t. Lambda 2t is a certain family of elements in the torus parameterized by real parameter. So we have here multiplication in the torus between lambda and lambda 2t, meaning that when we think of X as a field over torus, it is rotated. So we have a rotation. But there is also second ingredient, this inner automorphism, and we again see here this B-row operator. So the message here is that scaling automorphism at the level of direct integral can be seen as a rotation over the torus plus, or rather composed, with certain inner automorphisms. But this is enough to obtain the following results, that that all of the, well, that inner automorphism, inner scaling automorphisms and inner approximately inner scaling automorphisms are the same. I really have to hurry up, so let me go to our results. First of all, we were able to show, well, we were able to calculate all of these invariants. First, scaling the invariant when the scaling group is trivial does not depend on the group at all. It only depends on Q. However, maybe let's focus on the invariant of inner scaling automorphisms. It depends on certain number epsilon w. A very interesting feature. So then we wanted to calculate this number. You can justify that it is enough to look at simple case. So this is what we did. We by very concrete calculation, we calculated those numbers for simple G groups where the root system is irreducible, and we obtain a very interesting answer already in the SUQN case. So in this situation, let's look at SUQN plus 1. So that, we are in a n type situation. Then it turns out that this number is 1 or 2, depending on parity of n. In particular, when we look at SUQ3, we obtain that this number is equal to 2. And this is very interesting because of the following reason. We see that the two invariants of trivial scaling automorphisms and inner scaling automorphisms are different. This means that we obtain a non-trivial inner scaling automorphism, but we know more. We know that all of the irreducible representations of SUQNs, well, there is trivial representation which has dimension 1, but all of the rest have dimension at least 2, meaning that there are no group-like elements. So we obtain inner scaling automorphism which is not implemented by a group-like unitary, which I believe is quite interesting, as this is first situation of this behavior. In the previous example that we are able to construct, we use this by cross-product construction, but then you obtain inner scaling automorphisms by throwing them into cross-product. In particular, they are group-likes. So it was not at all not clear whether this kind of behavior can happen, and it is the case that it happens in SUQ3. And maybe just let me end with stating that, well, you can, for all of the rest simple cases, you can also compute those numbers. The previous result gives you all of the invariants, and you can also reduce situation of general semi-simple Lie groups with all of the injective to the simple case where we have complete answer. Okay, and as my time is up, I would like to end here. Thank you.
Thank you very much. Questions, comments, please.
I have a comment on this very last result, that an invariant very similar to the one we were considering had been considered before in the von Neumann framework used by Stefan Baas. And the thing is that he precisely looked at times t so that the scaling automorphism tau t is inner implemented by a unitary group-like element. And it wasn't clear at all that there is any difference between our invariant, which is looking at times t when the scaling automorphism tau t is inner, and his invariant. And it turns out that it was right under our noses, just one step from SUQ2, namely SUQ3, and any SUQn with odd n. So I find this rather interesting, because when Stefan introduced his invariant, he was absolutely convinced that every inner scaling automorphism is implemented by a group-like unitary. So this is a nice result that we have.
I think I should have said that, but I forgot.
Jacek, and how about quantum double torus? There is such a compact quantum group. What's your invariant then? And let me tell you why I'm asking this question, because, well, let me ask two questions at the same time. So the second question is, how about any example when this gamma omega or W is bigger than 2? Because it looks like either you have a log of Q or log of Q squared, right?
Yes, this I can answer.
Okay, so begin with this. Yeah. Mhm.
This I can answer because, well, in the simple case, as you say, either we obtain 1 or we obtain 2.
Mhm.
And what about general case? Well, we obtain the answer that we decompose root system into irreducible parts, and epsilon w is given by greatest common denominator or divisor. So we really obtain either 1 or 2. Turns out.
Okay, and so this is like log of Q or log of Q squared, right?
Yes, exactly.
And the reason why quantum double torus came to my mind, because we constructed this as a quantum group which renders the usual quantum torus a homogeneous space. And so we're looking for sort of quantum symmetry, linear quantum symmetry of a quantum torus. But there was this funny effect: if the deformation parameter of a quantum torus was Q, then in our construction of quantum double torus, the deformation parameter of this quantum part of a quantum double torus was always Q squared. So that's how this quantum group came to my mind. But anyway, my simple question to you is, can you tell me the invariant?
No, and yeah, so the simple answer is that we didn't look at this case, so no.
No, but I think we can.
Okay.
It's a CATS type quantum group.
Oh,
so everything is trivial.
Okay.
Okay, I forgot this.
Yeah,
thank you, Piotr.
Then definitely yes.
Yeah, thank you, Piotr.
So the invariants, some invariants were dependent on Q, but can we still say that as Q changes, they are isomorphic as fundamental, as C star level complex quantum group, or as they are isomorphic as complex quantum group?
Well, the von Neumann algebras definitely are isomorphic because of basically this result. The von Neumann algebras are simply given by this direct integral. For all GQ, they are given by this direct integral. So after isomorphic, this is simply tensor B of L2, tensor product L infinity of the torus. L infinity of the torus doesn't remember anything. So all of this, yes. So in particular, the rank isn't remembered. So all of the von Neumann algebras are the same. But when it comes to C-star algebras, that is definitely a good question. And I don't know. For SUQ2, yes, for SUQ2, the Q is not remembered by the C-star algebra. But whether similar thing is true for other Q deformations, I have not seen such a result. Yes, though maybe let me just say that there is a result that, for example, SUQ3 is not a graph C-star algebra, so it won't be isomorphic to C-star algebra of C of SUQ2. So maybe there is. So
SUQN, like, is it, are they isomorphic to the same higher rank graph?
Sorry, could you repeat?
So you somewhere said that in SUQ3, they are isomorphic to this higher rank graph test level. So is it the same test graph, higher rank graph algebra for each Q? That's what I'm asking.
That's a good question, and I don't know. And the reason that I don't know is that this result, well, I learned it from Marco Matassa. He writes it in his paper with Robert Junkan. But to my knowledge, Giselson, who proved that C of SUQ3 is high rank graph C-star algebra, I think it is not really available. At least it wasn't last time I checked. So I think so I don't want to speculate.
Thank you.
Well, I have a comment, but I actually am not sure. I think that the proof was that for SUQNs, they don't depend on Q, but I'm not right now, I'm not sure. But there is another comment that sort of came to me now, that this presentation for of our invariants for GQ might suggest that these invariants are always these subgroups, so they have to be some pi over log q times z or pi over log q squared times z, something like this. Well, yes, for q deformations. But in general, these invariants can be pretty much any, I mean, even in our previous paper, we have pretty much any group can be the tau t in invariant, t tau, sorry, the inner. So of course, these Q deformations are very special. And then, yes, as it looks right now, that looks, let's say, slightly boring, but so the only variation is the Q and whether this epsilon is 1 or 2, but that is the case for Q deformations, and these invariants can be quite different. That's, but for other examples, that is my comment.
So this T invariant you can calculate from modular.
Sorry, I didn't understand.
For modular automorphism group, can you calculate the T invariant? So here you calculate.
Yeah,
first
yeah,
scaling.
sure. Yeah, but this is okay. In this case of a compact quantum group with the C-star algebra type 1, the modular automorphisms are inner anyway. So in this case, it's not important. I mean, we know the invariant, it's R. But in other cases, it's different.
No more questions for the audience? No raised hands on Zoom. Okay, so let's thank the speaker.
Thank you.
Okay, so